In my today's lecture, I will start the next module, that is module 4, which is load flow analysis of radial distribution networks. Alternatively, it is also known as power flow analysis. Power flow analysis of radial distribution networks. Okay. So, this is an important tool to analyze this performance of a radial distribution network, and therefore, this is useful in operation and planning of power distribution systems or power distribution networks. Okay. So, that is why this module, although it is a very short module, I will need 2 lectures to complete, but this module is very important for any student or practicing engineer to understand the basic concept of power flow analysis, and this will be used as support subroutine of various power system research problems or solving various types of power system research problems. Okay. Whether it is a power system planning problem, whether it is a optimal operation of power distribution network problem. So, those areas this power flow analysis or load flow analysis is an essential tool. Okay. So, in this particular lecture, I will talk about this introduction of this optimization problem, then one important aspect, that is per unit conversion, which we require for analysis or for having this load flow or power flow analysis. Then this data preparation, which is another important aspect, and then basically this I will talk about a particular type of this power flow approach, which is backward forward sweep load flow or power flow algorithm. So, I will illustrate how it what do you mean by this load flow or power flow analysis, and what is forward and backward sweep load flow algorithm. And also I will show you some of the simulation studies for some typical distribution networks, the results that we got from this power flow analysis. Okay. Now, as I said, these load flow studies are performed to know the steady state operating condition of a power system, and that is why it is an important as tool for any type of power system problem, so as the distribution system problem. Okay. Now, this power system, power are the known quantities rather than the currents. So, the equations in load flow studies are in terms of power. Okay. So, these power flow equations are usually nonlinear and solved by iterative techniques, and we know that there are many power flow algorithms which exist for power system load flow studies, for example, Gauss Seidel, Newton Raphson, fast decouple, etcetera. Okay. So, those things are taught in electrical power system course. Okay. And as I said that this load flow studies are essential for this planning, operation and economic scheduling and exchange of power between the utilities. So, this is done by electrical utilities to facilitate several aspects their operational to have a better operation, to have a better exchange and all these things. Okay. So, they also require this type of studies of transient, contingency and stability. They are also used for those type of studies, we use load flow analysis. Okay. So, load flow analysis is also used for contingency analysis, which is very popular area of research in power system. Okay. Now, here for this particular lecture, I will focus on this forward backward sweep load flow algorithm or backward forward sweep load flow algorithm, which are essentially same meaning. Okay. And this is useful only for radial distribution networks. So, this is only useful for radial distribution networks, because as I said in module 2, I discussed that the difference of your radial distribution network with conventional power transmission systems. Okay. At the very beginning also I discussed. So, this particular load flow algorithm or power flow analysis is useful for radial distribution networks, and you know that distribution networks are radial only, they operated as radial, although we have a provision for tie lines which make it weakly mesh, but we use it as radial. Okay. Now, for this radial distribution networks, some of the conventional load flow approaches they do not work, okay, because they have some specific characteristics, particularly this radiality, another is R by X ratio is usually high in power distribution networks. So, that is why this conventional load flow approaches like Newton-Raphson load flow approach may not converge always. Okay. So, that is why researchers in who are working in power distribution system operation and planning, they propose a new approach which is called this forward backward sweep approach or backward forward sweep approach. So, this is a simply application of Kirchhoff's current law and Kirchhoff's voltage law. I will come to that. Okay. And this algorithm works for radial distribution network only. Okay. And it is very simple algorithm, it is very easy to implement in any programming language one knows. Okay. So, I will come to that. Now, before I show all these details of this slide, I will basically show you how do what is load flow approach or what is forward backward sweep load flow or power flow approach, and how it is applicable for power distribution networks. And in order to mention that, I will take a typical radial distribution network topology for example, and I will show you step by step how you will implement this approach or this algorithm to solve any kind of power distribution networks, whatever the number of nodes or buses might be. Okay. So, first this lecture or in order to start this forward backward sweep load flow algorithm or backward forward sweep load flow algorithm, first thing that you need to draw single line diagram of the distribution network. Draw single line diagram for typical distribution networks. For a typical distribution network, this is the first step that one need to follow. So, this is step 1. So, step 2 is prepare a data file which consists of the data of the typical power distribution network. Okay. Now, step 3 is choose appropriate base quantities. Okay. So, why we need that, I will come to that. Okay. Now, next step is to convert all the quantities to per unit quantities. Okay. And final step is start the load or power flow algorithm. That means, before I start discussing about this power flow approach or power flow algorithm or load flow algorithm, whatever you may call, there are some steps that I should follow. Okay. So, these are the steps. First, we need to draw or sketch the single line diagram of a typical distribution network, for which we are trying to develop this power flow algorithm or load flow algorithm. In fact, if you develop a power flow algorithm, that will work for any type of systems. I will come to that, but here in this particular lecture, I will focus on a typical simple typical radial distribution network topology, and I will show you step by step how do you solve or how do you go ahead to implement this approach. Okay. So, first step is draw the single line diagram for a typical distribution network, which needs this power flow approach. Okay. So, let me draw it first. So, suppose this is my substation, and I will call that this particular substation at node 1 or bus 1. Okay. Node 1 or bus 1. Then we have a single feeder. We have a single feeder which is having some few nodes. This is suppose one node, this is suppose another node, this is suppose another node. So, I can name this as node 2, this as node 3, this at node 4. These are the nodal points, okay, where we have this distribution transformers connected, and that distribution transformer is connected to the customers of these distribution networks. Okay. So, each of this node is having some load demand, and this load demand is shown over this arrow. So, this arrow shows this loads, okay, connected to the particular nodal point. Okay. Now, we also have some. So, this is a single feeder network, as you can understand. We have one substation located at node 1. In fact, in distribution network, we either use this terminology node or bus, okay. But usually we use this terminology node, because we use to represent this nodal point, because the same terminology is for similar concept to represent the same thing in power transmission system, we use this terminology bus. Okay. So, looking at this single line diagram. So, this is a single line diagram, you can understand, although we have drawn it a single line, but it is actually of 3 phase network, okay. And all these loads are also 3 phase loads. Okay. Now, this is a main feeder or trunk feeder, and we may have some lateral feeder or laterals like this. So, with bus number 2, we have another nodal point, that is node 5, which is having some load demand represented by this arrow. Similarly, with this node 3, we have another lateral feeder like this, and it is represented by bus 6, and this is what the arrow which represents the load demand. Okay. All right. And so, if you look at the single line diagram, as I said, all are of 3 phase. Okay, all are of 3 phase, and we represent them, all lines are of 3 phase, all loads are of 3 phase, and we represent them by these 3 parallel lines. But the single line diagram shows you the equivalent single phase form of a 3 phase network, I discussed long time before. Okay. So, if you look at this network, you will see we have 6 number of nodes. So, we can call it as a 6 node radial distribution network. Okay. So, it is a 6 node radial distribution network. Okay. And when you have a radial distribution network, if you have n number of nodes or buses, then there will have n minus 1 number of lines. So, if you look at this particular single line diagram of a typical distribution network or typical feeder of a distribution network. Here exist 5 lines or 5 distribution lines. One line is connecting this node 1 or substation to this node 2. This is one line. Another line is connecting node 2 to node 3. Another line is connecting node 3 to node 4. Another line is connected nodes 2 to node 5. Another line is connected between nodes 3 to node 6. Okay. So, we have 1, 2, 3, 4, 5 lines. So, for this is another thing that you should understand for a radial distribution network. With n number of nodes or buses, whatever you may call, we prefer these nodes, this terminology nodes. There are n minus numbers of distribution lines. Okay. Now, for a power distribution network, mostly all nodes are of these passive loads. So, they have some active power demand and they have some reactive power demand, and we can represent this load demand by something like that. For example, that for node 2 the active power demand let us say is P 2 and reactive power demand let us say Q 2. Okay. So, P plus j Q 2 is basically the load demand at this node 2. Okay. Similarly, at this node 3, this active and reactive power demand can be represented by as P 3 plus j Q 3. Similarly, at node 4, this active and reactive power demand can be represented by P 4 plus j Q 4. Okay. At node 5, this is represented by P 5 plus j Q 5. Okay. And at node 6, it is represented by P 6 plus j Q 6. Okay. Now, in power transmission system, there are different types of buses, different types of buses, okay, for power transmission systems. Okay. And we categorize them as slack bus, then load bus, then PV bus or voltage control bus, voltage controlled bus or PV bus. So, these are the typical types of buses. Okay. But for a passive distribution network, as long as there is no source connected to the network, we only have two types of buses. One is called slack bus, another is called load bus. So, here you can see we have one number of slack bus, that is we consider that reference, and that is of course, this substation bus. So, this is slack bus we will consider, who is basically importing power to all other nodes. Okay. And rest of all these nodes are, or all these buses are of load buses. So, they are connected to the customers, and they these nodes are having some active power demand and reactive power demand, which are represented by P 2, Q 2, P 5, Q 5 this. Okay. Now, what is that goal of this power flow analysis or power flow solutions? So, our goal is to find the, to determine the unknown quantity, to determine the unknown quantities. Okay. Now, what are the unknown quantities? We have for slack bus, usually its voltage and angle V and delta voltage magnitudes and angle are specified. Okay. So, for slack bus we know that magnitude of the voltage and its angle, okay. And this power and active and reactive power which are flowing away from this slack bus are unknown quantities. But for load buses, as you have seen, this power demand is specified, P and Q, active and reactive power demands are specified. So, the unknown quantities are voltage and this angle. So, basically this goal of this power flow analysis is to determine the voltage, magnitude and the angle of all these load buses. Okay. Having this slack bus voltage and angle known, let us consider this voltage is represented by 1 per unit at an angle 0 degree or 0 per unit. Considering that, we need to find out what would be the voltage of all these different nodal points or different nodes. So, our goal is to find out this V 2 phasor, that means magnitude of V 2 as well as its angle. So, this is one unknown quantity. Then similarly, for nodal point 3, V 3 is our unknown quantities. Similarly, at bus or node 4, V 4 is our unknown quantities. For bus 5 or node 5, V 5 is our unknown quantity, and for 6, V 6 is our unknown quantities. So, our goal is to determine this V 2, V 3, V 4, V 5, V 6. Okay. So, I have drawn in phasor form, I have written in phasor form to indicate that we need to know that what would be the voltage magnitudes as well as angles of these load buses. So, this is our goal. So, that is why we will perform this load flow analysis. Okay. So, in load flow analysis we know that some of the quantities are known and some of the quantities are unknown. For load buses, the quantities known are this active and reactive power demand, and the unknown quantities are this voltage and the angle, voltage magnitudes and the angle. So, we will determine this with this load flow. Okay. So, now we have completed this step 1 only, and we will need to go to this step 2, that is we need to prepare a data file. Okay. We know that some of the data, one is as I have shown you, that active power and reactive power demands of the load buses. Another things that we will know, that is basically these line parameters. So, let us represent this line parameter as R 12 plus J x 12. So, where R 12 represents this line resistance for the line which is connecting this node 1 to node 2. Similarly, x 12 is representing the line reactance which is connecting this node 1 and node 2. Okay. Now, since this distribution line is already existing, we know that what would be the line parameters. So, we from this conductor specification we can find out that what would be the line resistance, and we also know that what is the length of the line. Usually conductors are specified that much of ohm per unit length. So, if you multiply this length of the particular line with this R, that is resistance per unit length, so you will basically get the resistance of that particular line. So, similarly, we also know that this line parameters of all the lines. For example, line connecting this node 2 to node 3, its parameter, let us write it as R 23 plus J x 23. Similarly, for this line which is connecting node 3 and node 4, the line parameters are R 34 plus J x 34. Okay. For this line which is connecting node 2 to node 5, line parameters we can write it as R 25 plus J x 25. Similarly, for this line we can write it as R 36 plus j x 36. Okay. So, these line parameters are known to us. So, we need to determine these voltages with the information of line parameters as well as the information of this active and reactive power demand of the load buses. But apart from that, we also know the network topology, how this network is connected by drawing this single line diagram. This is also having an important knowledge. Without that we cannot go ahead. Okay. Now, let us see how can we systematically present these known and unknown quantities to create a data file. Okay. So, in next page I will show you how to create data file. Data file creation, let us say. So, we will create two data file, one is the node data, another is line data. Okay. Now, let us first start with node data. In node data, we know that we have total we have 6 number of nodes. So, let us create a node data or bus data file, which is for the 6 number of nodes. Okay. Okay. The first column that I wish to keep as this node number. Okay. So, we have 6 different numbers of nodes, you can see that 6 node system it is. So, we can write node number as 1, 2, 3, 4, 5 and 6. Okay. Now, next we will keep as that what type of the node we have type. Okay. So, this is basically this shows that categorization or classification of the nodes. Okay. As I said, in passive power distribution network, radial distribution network, we have two different types of nodes, one is called slack bus or slack node, another is called load node. So, let us represent this node type either by 1 or by 0. 1 means it is of slack node and rest are load node. So, type 1 represent slack node and type 0 represents load node. Okay. Then we will be having the informations of bus or node voltage and magnitude. So, V magnitude, okay, and angle. Okay. So, angle can be in per unit or in degree. So, this V we represent in per unit and it can be also represented by per unit. What is per unit? I will come to that, okay, and how to convert this in per unit, all these things. Okay. And as we know this for slack bus or slack node, this voltage and angles are specified. These are known quantities. So, I can write them as 1 at an angle 0. For other nodes, we do not know what is the value of this V and delta, and we are supposed to determine this. Okay. And that is what our goal for this load flow approach. Now, we know another two quantities which we will write is write it in column 5th and column 6th, which is active power demand, Usually, this is in kilowatt for distribution networks, because distribution networks load are in kilowatt level, not in megawatt or watt. Okay. Similarly, reactive power demand. It is normally represented as kVAR. Okay. Now, for slack bus it is not a load bus. So, active and reactive power demands are not there, but for all other buses we know active and reactive power demands. So, we can write for example, for node 2 this active power demand is P 2, reactive power demand is Q 2. For node 3, active power demand is P 3, reactive power demand is Q 3. For node 4, active power demand is P 4, reactive power demand is Q 4. For node 5, P 5, Q 5. For node 6, P 6, Q 6. Okay. So, this will make this bus or node data. So, these are the data available to us, and only thing is that we need to know that what is that voltage and angle of this load buses. These are unknown quantities. Okay. So, I put this sign so that question mark, so that this will derive. Okay. Now, apart from that, as I have shown you, as I have told you, we know some of the data here. One is line parameter. So, this line data will represent it another table. So, for line data, we will prepare another table. Okay. Now, as we have discussed, for a 6 node system, we have 5 numbers of line. Okay. So, the first 2 columns we will keep to know that these lines are connected to which node to what node. Okay. For example, so this is called, let us say, N S sending end node, and this is, let us call it N R, where N S is sending end node, and N R is receiving end node. Because as you know, in radial distribution networks, power is flowing unidirectionally. So, power always flow from 1 to 2. So, for line this 1 to 2, its sending end node is 1, receiving end node is 2. So, I can write is N S 1, N R 2, and there are 2 other columns which represents line resistance, which is normally represented in ohm, and line reactance, which is also represented by ohm. So, for this line which is connecting node 1 to node 2, line resistance is represented by, let us say, R 1 2, and line reactance is represented by X 1 2. Similarly, the next line is between these nodes 2 to node 3. So, we write it node 2 to node 3, and corresponding resistance and reactances we write R 23, X 23. Similarly, the next line is between nodes 3 and 4. So, I write it 3 and 4, R 34, X 34. Similarly, this is another line which is connecting nodes 2 and node 5. So, I can write 2 5, this is R 25, X 25. Okay. And similarly, there is another line which is connecting nodes 3 and node 6. This is another lateral line. So, 3 to 6, R 36, X 36. Okay. So, these are the informations which known to us, and in line data all quantities are known. So, these all quantities are known. So, these are known quantities, and these are the unknown quantities here. So, unknown quantities are V per unit and delta per unit for load nodes. So, these are unknown quantities. These are unknown quantities, and our goal for doing this whole analysis is to find out the magnitudes of these unknown quantities only. So, we are intending to find out this V and delta for this load nodes. Okay. Now, with the preparation of this bus data file and line data file, or bus data table or node data table or line data table, we have completed this step 2. Okay. So, this is an important part of understanding this forward backward sweep load flow approach. We have not started the algorithm so far. Okay. So, we are in the process of creating data file only. Now, the next step would be to choose appropriate base quantities. Next step should be to choose appropriate base quantities, and next two steps are to choose appropriate base quantities and convert all the specified quantities to per unit quantities. Okay. So, this per unit conversion is an essential thing in any sort of power system calculation. Okay. So, it not only makes the calculation easier, but also it has several advantages. I will talk in my next lecture. Okay. So, now in order to convert this per unit quantities, what we will do? We have to choose base quantities. Okay. Now, what are the base quantities we require? We need two base quantities. One is base voltage, okay. Another is base volt ampere. So, this volt ampere we represent either kilovolt ampere or MVA megavolt ampere. Okay. Now, how do you choose their values? This base voltage is usually chosen considering the system voltage. Okay. For 11 kV system, so we consider this base voltage as 11 kV, and whatever voltage values we have, we will convert all by normalizing with this base voltage, that is in terms of this 11 kV. Okay. So, 1 per unit voltage represents it is a 11 kV voltage. Similarly, base MVA we choose 10 MVA or 1 MVA or 100 MVA according to the power demand. Okay. So, after this selecting these base quantities, we need to convert all quantities into per unit quantities. Okay. So, how do you convert this? It is very easy, as you know, in order to convert this active power to this per unit. So, let us write it P 2 per unit will be equal to actual value of P 2 divided by this base MVA or MVA base. Okay. So, this base MVA we write it as MVA base. Okay. Similarly, this base kV we write it as kV base. Okay. Similarly, all this reactive power will be converted to per unit by normalizing with this MVA base. All right. Similarly, all the voltages actual this V 2 per unit will be actual voltage divided by this base kV. Okay. So, by dividing by normalizing with this base quantities, we will convert this kilowatt and kVAr to the per unit. Okay. Similarly, we also know the this line reactance and line resistance. These quantities also you need to convert to per unit. Okay. Now, in order to convert to this resistance to per per unit, let us find out this base impedance, that is ZB. Okay. Base impedance. So, how do you find this ZB? ZB you know it is VB divided by IB. So, base value divided by base current. So, if you multiply this numerator and denominator with this V, so what we will get? VB square divided by VB IB. Okay. So, it is basically a this Z base or base impedance is a ratio of base voltage square to the volt ampere base. Okay. Now, we know that here we have this base voltage in kV and volt ampere base in MVA. Now, we can also write it as a this is equal to k VB square divided by MVA B, because if you multiply this k VB kilovolt means 2 kilovolt quantities, effectively it will result in 10 to the power 6 in the numerator, and this if your denominator is in MVA, this is nothing but actual quantity multiplied by 10 to the power 6. So, those 10 to the power 6 will cancel out from numerator and denominator, which makes your ZB in ohm. Okay. So, this is in ohm. So, once we get this base impedance, so what we can do? We convert all this line resistance into per unit by normalizing with this base impedance and also line reactances as well. So, this R 12 per unit will be actual value of R 12 in ohm divided by this Z base. Okay. Similarly, X 12 per unit will be actual value of X 12 in ohm line reactance divided by Z base. Okay. Now, you convert all this ohm to per unit before starting your load flow algorithm. Similarly, all kilowatt active power demand into per unit and all kVAR reactive power demand into per unit before you start this load flow program. Okay. So, this is the simple step one need to understand. When you prepare these two files, you need not to remember this network structure every time. You need not to remember this network structure, rather these two data file will provide you all information related to your network topology, related to your network load demand, related to whatever you want about this network. Okay. Now, in fact, this topology is you can trace out from this information of the sending end and receiving end node. Okay. Similarly, this bus or node voltages these are unknown quantities, but node active and reactive power demand you can get from this node data information. Similarly, line parameters you get from this line data information. So, the objective of preparing this table is to translate all this information or to convert all this information in a typical data file, from which one needs the access to write down the program codes for solving this. Now, so far I did not discuss how do we solve this power flow approach. Let us discuss right now. Okay. So, next step, as I said, we will start this load flow or power flow algorithm. So, we will write backward forward sweep or forward backward sweep, both are used in literature, backward forward sweep load flow approach. Okay. Backward forward sweep load flow approach. So, in backward forward sweep load flow approach, we have two major steps. One is called backward sweep, another is forward sweep. So, this is backward sweep for example, and this is forward sweep. These are sequential steps, and we need to first perform this for backward sweep and then forward sweep. Forward sweep is very easy to understand. Okay. Backward sweep is bit complex, but it is not as complex as the other type of load flow algorithm. Okay. Now, in backward sweep, we basically our objective is to determine the line current. Okay. So, here we have a concept of load current, another is line current. This load current is the current drawn. This one particular load is drawing what current is that the load current of that particular node. Okay. So, it is represented by I L bar. This bar represents that it is a phasor quantity. Of course, all voltage currents are of phasor quantity. Similarly, this line current is represented by only I bar. Okay. So, that is not standard nomenclature, again I am using here, so that you can differentiate this load current and line. So, basically if I go back and show you in that figure, then you can understand this difference of this load current and line current. These line currents are what current is flowing through this. So, these are the line currents. So, these are represented by I 12 bar, I 2 3 bar, then I 3 4 bar and so on. Okay. So, here I 2 5 bar and here I 3 6 bar. So, these are this I 1 2 bar, I 2 3 bar, these are basically line current. These are basically line current. Okay. And this load currents are the current drawn by this load. Let us represent in red color. So, load current is basically I L 2. So, what current is drawn by this load which is connected this node 2. Similarly, I L 3, I L 4, I L 5 and I L 6. This is I L 6. Okay. So, this I L 2 to I L 6, I L 6 they are load current. Okay. Now, this line current are function of load current only. So, load current is the current drawn by a particular load and line current is current flowing through a particular distribution line. Obviously, this if we apply KCL at any of the nodes, this line current would be function of this load current. So, a load current we can easily determine and then we will determine this line current with the simple application of Kirchhoff's current law. How to do that? Let us see. First, how do you find out this load current? As you know, this we know that V phasor I phasor conjugate is equal to I L phasor I am writing, because it is related to this load current. This is equal to P plus J Q. Okay. So, we can write it as V phasor conjugate I L. I L is representing this line current is equal to P minus J Q. So, I can find out I L is equal to P minus J Q divided by V star. So, this is how we can find out this load current. This is how we can find out load current. So, we can find out this load current for all these locations, because we know this P and Q for all these locations. Let us write it like I L 2 is equal to P 2 per unit, because we already converted this power into per unit, minus J Q 2 per unit divided by V 2 star. Okay. Similarly, we will determine all other load current. I L 6 will be equal to P 6 per unit minus J Q 6 per unit divided by V 6. V 2, V 6 they are already in per unit. So, I am not writing. So, all quantities are per unit and which will result in this line current, they are also in per unit. Okay. So, they are in per unit. So, they will lie within 0 to 1, they are fractional quantity. Okay. So, we will determine this load current and line current with the available information for P, Q and V. Now, you can see that here our V are unknown, this V 2, V 3, V 4, V 5, V 6, these are unknown. So, what we will do? How to find this load current then? Because we need the information of voltages here. Okay. So, since as I said this algorithm or power flow approach is of iterative approach, we will initially will choose an initial guess values of these unknown quantities. So, we will choose the initial guess values, and this guess value we make a flat start, meaning that we assume that the initial guess for all these bus voltages or node voltages are 1 per unit and these angles are 0. Okay. So, these are not actual value, this is basically our guess value. or initial value. Okay. So, we assume that all these voltages, initial means at the iteration 1, because when some quantities are unknown, if we cannot determine it directly, then we will determine it indirectly, and that indirect determination is an iterative determination. Okay. So, we will start with some iteration count, let us say iteration 1, and then slowly we will update this guess values. So, for iteration 1 we assume that this all unknown voltages are of 1 per unit and all unknown angles are of 0 per unit. Okay. That means, voltages and angles are of 1 at an angle 0 per unit each. Okay. So, that means, for initial iteration we consider V 2 star is equal to 1, because it is 0 per unit angle. So, V 6 is equal to 1 and so on. Now, next we will determine this line current. Okay. How do you determine this line current? Line current. Now, determination of line current needs the application of Kirchhoff's current law, KCL, application of Kirchhoff's current law. Okay. Now, how do we apply this Kirchhoff's current law here? So, here for this determination of line current, we will start from the end nodes or terminal nodes. Okay. So, we will start with end nodes or terminal nodes. Okay. Now, that means, we will start with this terminal node either from 4 or from 5 or from 6. Why we will do so? I will come to that. Okay. So, since in our line data matrix our last entry is 6. So, we can start with 6 or then 5, then 4 and so on. So, for this 6th node, this current which is flowing through this node 3 to node 6, that is I 3 6 will be equal to this I L if you apply KCL at this nodal point, that is at node 6. So, what we will get? We will get I 3 6, that is the line current which is flowing from nodes 3 to 6 is equal to I L 6. This we get applying KCL at node 6. Okay. So, as I said, line current calculation is simply application of KCL. Similarly, next I will come to this node 5, which is again the terminal node, because there is no node connected with that. So, what we will do? We will apply this KCL at this point, and application of KCL says that this I 2 5 will be equal to I L 5. So, we can write it as I 2 5 is equal to I L 5. Okay. Again we apply KCL at node 5. Similarly, we apply again this KCL at this node 4. Node 4 is again this terminal node, there is no node connected beyond. So, what we can do? We write is node line current, that is 3 to 4 is equal to I L 4. If we apply KCL over here, that I 3 4 is equal to I L 4, I 3 4 is equal to I L 4. This is also application of KCL at node 4. Now, again we apply this KCL at node 3. So, this will give you this line current which is entering through this node, that is I 2 3 this. So, this will be equal to, if we apply KCL at node 3, this will be equal to this line, that summation of this outgoing current, that is I 3 6 and I L 3 and I 3 4. So, what we can write? I 2 3 is equal to I L 3 plus this I 3 6 and I 3 4. I 3 4 plus I 3, 6. This is again by applying this KCL at node 3. Then I 1 2 also we can determine this will be I L 2 plus if we apply KCL at this node 2, this will be equal I 1 2 will be equal to I L 2 plus this current that I 2 3 plus I 2 5, that is I 2 3 plus I 2 5. All right. Okay. Now, this is how we compute this all this line current. These are all in per unit. These are all in per unit. Okay. So, this is how we calculate this all this line current. Okay. And this line current calculation is somewhat complex term for this for backward sweep analysis, as I said. Okay. And there are many approaches for this determination of line current by using some algorithm or iterative way. Okay. So, in one approach this the nodes beyond a node are traced a priori, okay, and accordingly they determine this line current. Okay. For example, in fact, this is possible from this line data information or from this topology. We know that beyond this node 2 we have node 3, node 4, node 5 and node 6. That means, all these nodes power demand is flowing through this node 2. So, beyond this node 2, we have node 3, 4, 5 and 6, and beyond this node 3 we have node 4 and node 6. Okay. So, beyond this node 3 we have node 4 and node 6, and node 4, node 5 and node 6, they are terminal nodes. So, beyond that there is no node, these are void. Okay. So, these are terminals, n nodes. So, there are no nodes beyond that. Okay. So, once you can trace this, then your task to determine this current line current would be easier. Okay. Because this is this does not need any iterative approach, only you need to know that determine this we need to trace what are the nodes are beyond a particular node, and with this available information you can find out this line current. How? For example, this when you trace that beyond node 2, this node 3, node 4, node 5 and node 6 are there, then this power or current which is flowing through this node 2 will be sum of the load current of node 2 itself along with node 3, node 4, node 5 and node 6. Okay. How? Let us see. Suppose this I L 2 is equal to I L 2 plus I 2 3 plus I 2 5. So, this we can write it as I L 2 and I 2 3 is equal to I L 3 plus I 3 4 is equal to I L 4 plus I 3 6 is basically equal to I L 6 and I 2 5 is basically equal to I L 5. Okay. So, you see that this current which is flowing through this node 2 is sum of the all load currents which are beyond this node 2 along with its own node current, that is I L 2. So, it is summation of I L 2 plus I L 3, I L 4, I L 5 and I L 6. Okay. Similarly, this for I 2 3 also you can find out as this is equal to I L 3 plus I 3 4 is equal to I L 4 plus I 3 6 is equal to I L 6. So, once you find out that beyond this node 3 only we have these two nodes 4 and 6. So, this current which is flowing through this node 3 will be equal to sum of this load current of node 4, node 6 and its own node current, that is I L 3, I L 3, I L 4, I L 6. And since these are the terminal nodes, they are for these n nodes their line current is individual their load currents only. So, this is one approach by which one can trace this the nodes beyond a particular node, and accordingly after that you need not to have this information of network topology, and you can eventually find out what would be the line current or what would be the current flowing through that particular node. Okay. Now, similarly, this is one approach. Okay. Another approach is from this this NS and NR information, one can find out this line current. Okay. How one is find out this line current? Let us first start with this N node, that is node 6. You find that node 6 is the receiving end of one particular line, and then you find out who is the sending end side of that particular node, that is node 3. Okay. Now, after that you will determine this line current which is flowing from 3 to 6 for that particular line. Now, after that you check whether this 6 node is appearing at least any time in the sending end side, but you see there is no node 6 at the sending end. So, if so, then we can understand that node 6 is a terminal node or N node, and its line current between 3 to 6 is equal to the load current of the node 6. Now, after that you forward to the next row, that is at node 5. Again you check whether node 5 is appearing any time at the sending end side. No, it is not appearing. So, again node 5 is also a terminal node, and its current that is flowing through this node 2 to 5 is basically the load current of node 5 only. Okay. Then go to the next stage, that is you find this line 3 to 4, where again this node 4 is a terminal node. Why? Because it is not appearing any time in the sending end side. Okay. So, any node which is not appearing at the sending end side, of course, is the terminal node. So, the line current that I 3 4 is basically equal to the load current of this 4. Okay. Then you go to the next step, that is you look at this node 3. So, this is the line I 2 3 which is having this receiving end side at node 3. Now, you see whether node 3 is appearing any time in the sending end side. Yes, it is appearing at least twice, okay? At least once, that is between 2 to 5. So, when it appears, then you along with this line current along with this load current of node 3, you also count this load current of node 5, which is the receiving end side of this node 2. Okay. Sorry, not 5, it should be 4, because 3 is appearing here in the sending end, and corresponding this receiving end side is 4. So, for this calculation of I 2 3, your load current of I 3 as well as load current of I L 4 should be counted, and also you see whether 4 is appearing any time in the sending end. So, it is no, answer is no. So, 4 is not any, 4 is not having any receiving end side. So, it is a terminal node. So, basically this I 2 3 is equal to I L 3 plus I L 4. So, you can check whether it is true or not. So, it is equal to I L 3 plus I L 4. Okay. So, this 3 is again appearing twice, as I said, one is node 4, another is node 6. So, you have to add this both this load line current, that is I L 4, I L 6 and I L 3 in order to compute this current flowing through this line 2 to 3 and so on. So, this is how also one can trace this line current. Okay. Now, once you have traced this line current, then your task of this backward sweep is over. Then you come to this forward sweep. Forward sweep is to compute or to determine bus voltage, okay. And this is by application of KVL, and that will flow through the forward direction. Why in previous case it was backward direction? Because you see, in order to find how much current will flow through this line 1 to 2, I need to know that how much current is flowing through this node 3, node 4, node 5 and node 6. So, I need to find out those currents who are independent, and that is why we start it from the terminal nodes, because this current, this I L 2, I 12, it is a function of all these load currents. So, you cannot determine this value of this without determination of individual load current or individual line current. Okay. But this I 34, it is independent of the loads of node 2, node 3, node 5, node 6. So, you can easily determine with simply the information of this load of the node 4. Okay. So, that is why this backward sweep is done in the backward direction. While this forward direction, this will do the forward sweep, because we know the substation voltage, it is specified to be 1 at an angle per 0. So, I can simply calculate this voltage V 2 by subtracting this drop from this V 1, and this drop is basically happens due to this at this line 1 to 2. So, it is equal to I 1 to 2 multiplied by R 1 2 per unit plus j x 1 2 per unit. Okay. Similarly, you calculate for all, we do it for all. We can calculate this end, that is end node, that is 6th bus voltage, simply subtracting that V 3 with this voltage drop, that is I 36. So, simply we get V 6 is equal to V 3 minus I 36 multiplied by R 36 per unit plus j 36 j x 36 per unit. So, similarly, we can calculate, this is very easy step, there is no any sort of this is very easy, not at all complex, simple straightforward. You need not to have any problem for determination of this, because once you get this line current and this line parameters are already known, we can eventually find out these voltages. And when we get these voltages we need to update here, we need to update in the guess value. Okay. And we need to keep on this updatation till we get some converged value of this unknown voltages. Okay. So, here we will have some convergence criteria, which is normally the voltage error, the error minimum value of maximum error. So, max error and that if we achieve that, if we achieve this convergence criteria, we can say that load flow is converged. Okay. So, I will stop at this point today. We will discuss the results and other aspect in the next lecture. Okay. Thank you.